the first part of the talk will be, the idea of the talk is very simple. We'll be studying black holes and how classical black hole geometries are affected by quantum fields that are present in the background. And it's also very old, but it turns out that we'll have some interesting things to say, or maybe some results that will be of interest to some of you. So indeed, so the first part of the talk I will be dealing with. In the first part of the talk I'll be talking about black holes in 4 dimensions, which I have talked about before. Some of you have heard about it, but in the later half I'll talk about some 2D cases where we have some new results. So probably those will be new to you. This work has been done in collaboration with Sergei Solodukhin over the last few years and his students. So as I said, this idea that I'll be talking about, it's very old. We know that horizons are key feature of black holes. They provide deep insights. But these classical black hole solutions can be modified in various ways. And we'll be talking about in this semi-classical regime where we have quantized matter fields. You can of course also have some fuzzball-like pictures in quantum gravity and so on, but we'll not be worrying ourselves with that. So we'll try to understand in the semi-classical regime quote-unquote non-perturbative effects or fate of black hole horizons. And our motivation is, or at least my motivation is mainly from black hole information problem. And there are so many things to say about black hole information problem that it's better not to say anything, but rather I'll just serve my purpose and give a random, well, not so random paper from history. So for example, this paper from 2005, they were taking some ad hoc solution. So at that time, Maldasena's paper came out where he was studying 2-point functions in black hole geometries, the fact that the decay over time, and that was the information loss. And you are trying to see that whether there are small quasi-periodic fluctuations at the late times. So those features people were trying to reproduce in various ways. And one of such papers was that they took it's a cartoon picture, but they took a situation, a geometry, where the black hole horizon is replaced by a small non-zero throat, which I have tried to depict here, and then maybe on both sides it goes to some asymptotically flat geometry or whatever. Okay, so it was some some ad hoc geometry that they considered, and they were able to show that they reproduced late time quasi-periodic oscillations instead of an exponential decay. So in this in this talk, what we will see that in some cases you indeed have a very non-trivial modification of black hole geometries purely under these semi-classical considerations. Maybe sometimes even like this. Yeah. Sorry. Well, yeah, it will be great if we can find it as a solution, but at that time for sure they had no idea. That whether it comes as a solution or not. So yeah, as I said, for the first part I'll be talking in 4 dimensions, and then we'll have a more analytical handle of the situation when we go to 2 dimension. And I will be talking about RST model as opposed to JT model, and we will see that when we talk in 2 dimensions, we'll do things exactly. We could do it exactly. In 4 dimensions, we have to use many. We have to take some assumptions. We have to do some local analysis near horizon and so on. So it's incomplete, but of course 4 dimensions it is more interesting. So we will first study 4-dimension, 2-dimensional cases, black hole cases in classical, GR, then we'll study these properties in semi-classical GR and see what happens there, and then we'll draw some conclusions. So okay, let's start with 4D. So our setup for 4 dimensions is that, so as I said, 4 dimension is hard to compute, the effects of the quantum fields. You have to compute some sort of effective action, one loop effective action, higher loop effective actions, and so on. And so some ansatz will come in handy. We can only do it in a very specific scenario. So our setup will be static, spherically symmetric, asymptotically flat black holes in 4 space-time dimensions. We will consider back reactions from quantized scalar, gauge, and fermionic fields. In some sense it's non-perturbative because we will be only considering free fields. So the results will be one loop exact. But our analysis will be near horizon because of the technical challenges. We can do some numerical stuff, and I try to do that as well, but I'll not be talking about that. In 4 dimensions, our main goal, as I said, that our non-perturbative handle will be because of free fields, and we'll be talking about conformal anomaly and conformal anomaly induced effective action. So the thing is that if you remember that in 4 dimensions the main problem with the effective action which is induced from conformal anomaly is that the action is not fixed, the effective action is not fixed. You only fix it up to a conformal factor. So that's why there is a thing called anomaly induced effective action, which is known but not the full effective action. But we will fix this factor by casting the space-time in a conformal form, okay, and by going near horizon. So yeah, so we'll start with a general ansatz of this kind. So it's in a conformal factor form, so omega square z, and then this part of the metric looks like this. And then we will, so of course the solution is Schwarzschild, but we will pose the problem in a way which will help us analyze the equations when we take the back reaction effects into account. So you can check that the 2 independent Einstein's equation take this form. So I have gone to a new coordinate system by multiplying r with omega here, e to the sigma. And from here one can say, and it's true quite generally, that if at some value of the radial coordinate, if r prime is 0, the sphere is minimal, then there exists necessarily a horizon. So this you can find from here, meaning that the GTT component of the metric, it's minimal.
So okay, sorry, yeah.
Not, this is just classical, yeah, right now. So we will study this aspect. So this aspect is true in, of course, for Schwarzschild black hole. We'll study this aspect, as I said, again when I add matter. The second aspect I'll be studying is by going near horizon. One can do, from Schwarzschild, you can expand Schwarzschild metric, you can go to do some coordinate transformation and put it in this form, where the corresponding omega and r takes these values, where beta inverse is the temperature. Horizon is located in these coordinates as z going to infinity. And then, of course, because it's a solution for classical GR, so you will say that, okay, if I have obtained the same classical solution, then it must be true that to leading order, well, these dot dot dots are the subleading orders as you go away from the horizon. So to leading order, yeah.
What did you mean by the previous slide that r prime is 0 for Schwarzschild?
No, I simply meant that r prime, if r prime is 0, then this equation tells you that omega must be 0. So GTT goes to 0. So at the horizon, it's a minimal area surface. And of course, this is also true that near horizon, in appropriate coordinate system, this satisfies the Einstein's equation. Okay. these factors of omega, I mean these particular parametrization of omega and r. So we'll test the validity of these two aspects within semiclassical physics, where by semiclassical physics I'll have in mind integrating out conformal anomaly in such a way that we have not just the anomaly induced effective action but the full effective action. Okay. So yeah, just a glimpse of the effective action that you have here. So now I have, in this slide I have taken into account, I have condensed many calculations, taken into account matter fields which are in here, A, B, which depends on the numbers of scalars and spin half fields, spin 1 fields. This effective action, anomaly induced effective action, is given in terms of these factors that you had in the answers, sigma z, n of z, r of z, and so on. And this last piece, 4 pi beta inverse gamma 0 of g mu nu, it's the part that you could not fix, which comes from the effective action from inside this bracket, okay, for this metric. Okay.
Just show that anomaly in this part, that should be a non-local action. Right?
Yes, this is, yeah.
Maybe you're in conformal gauge.
If you integrate out, yeah.
Integrate out what?
Sigma. You need to integrate out the relay target.
No. Even with the sigma, right? You should get something like R proximus R, where the R includes the sigma.
You can make for example, the Polyakov local.
Yeah.
You can. But is that what you've done?
So this is of course in 4 dimensions, but it's in a form that is local, very similar to Polyakov. We will also have the Polyakov later on. Yeah.
And have you included spin 2 gravitons?
Yes. No. Spin 2, no.
And why not? When you're working in some semi-classical.
Yeah, I probably should have. Yes. Yeah. No, it's. I think there are papers which have spin 2 effects as well. Yes. This we actually checked later that it exists in literature.
I think the motivation here was to think in terms of the boundary CFT, where you don't have a spin.
No, nothing like that. No. I have.
When these weren't lifted, I mean, hung mass and most small thing were probably looking at.
So I mentioned this paper because they had some expressions of this part of the effective action. Yeah.
I mean, you'd be interested in what all this does near the horizon or something, right?
Ultimately, right now it is exactly. So the problem was initially, this is what I want to emphasize, is that for example these old papers, Rigard, Birel, Davis, you only knew this anomaly induced effective action, and you can think of the fact that you cannot fix the conformal factor, the conformal part of the effective action is as if when you are integrating the conformal anomaly there is this integration constant. And this gamma 0 is essentially putting a boundary condition and fixing that integral. That for your metric with conformal factor omega equal to 1, your effective action gamma is gamma 0, and that's basically fixing everything. So this is difficult to compute in general. This paper by Gusev Zelnikov, they have an expansion in powers of omega. However, if you do a near horizon analysis, you can actually truncate that effective action and work exactly, and that just becomes these two terms. So this is why this became near horizon, where this arbitrary 3 manifold is now some hyperbolic space. Okay.
It isn't a universal thing, right? You could have all kinds of quantum states.
So
Dependence on the state.
Indeed. So what turns out is that this is for the Boole-Wire state. So you can, for example, do the entire analysis in a different state like Hartle-Hawking state, and you will get a different result. But yeah, I was coming to the state a bit later for in the 2D context, but you are absolutely right. Yeah. Okay, so the idea now is very simple. We have some effective action, free fields, got an effective action, we solve them and see what solution they give us. Okay. So first we'll study this aspect B. So you can plug in these answers and you can check whether these near horizon solutions that you had for Schwarzschild is still a solution of this effective action or not. So you take this entire thing, you vary them with respect to your variables, and you can check that even though one of the solution is satisfies, the other is not satisfied. Although curiously these equations will be satisfied, in fact even with this dots present. So not only near horizon, but as you go away from it for n equals to 4 super Yang-Mills theory, just because of the number of n0, n-half and n1 that appears in n equals to 4 super Yang-Mills theory.
N equals 4 in the bulk.
In the bulk, yeah.
Is it it's just because it's conformally inverse? You're not really using that.
No. I think there are some papers by Emparan on this. Yeah, I don't have much to say about that. About this. So the first lesson to learn then is that at least in a near horizon analysis, you see that Schwarzschild is not a solution of this effective action.
So, but what if you are working with Hartle-Hawking?
Then it will be. Yeah.
You are kind of putting the answer in that.
Right, absolutely. Yeah. I mean, Hartle-Hawking state also does various other things. We'll see in 2D. In 4D at least, it does satisfy. Indeed. I'm not. I'm not claiming that in all states something generic happens. Yeah.
I mean, in fact, you expect the horizon to become a bad place, right?
Yeah. But actually in 2D, you have also worked on it. I mean, even you do work with Boulevard states also.
Not usually. No, I haven't done that yet.
No, I will cite your paper.
It's 35 years, but I don't think so.
Okay, no, but okay. Something related. Yeah. No, at least in 2D case, for example, you can study particles in Boulevard state, and then it can effectively serve as a description of evaporating black holes. We'll talk about it. And this is also, in fact, those types of these what I just mentioned about Boulevard states were also discussed recently by Strominger and Hartmann in the calculations of islands. So it's just a 4D version of that.
You come to it, but in the RST model, certainly when we studied it, the Unruh and the Hartle-Hawking are the well-behaved states. Right? I mean, the stress tensor blows up at the horizon and the polar back.
Yeah, but
Okay, go on.
Yeah. But I think, maybe we discuss it when we get there. So I'm just to make sure, I'm just trying to enumerate the cases where we can solve and see what the geometries look like. I'm not claiming anything more, anything less.
I think the point is that, like, in a specific vacuum, it's also a specific state that above the horizon already.
Of course,
That's
yeah.
the reason why
Yeah.
I mean, you can solve it in this case, but it is ultimately you have already put in the prejudice.
Yeah, but sometimes you will see that the effects are such that there exists some sort of, as I said, in 2D you will have a nice black hole evaporating geometry which people have studied. You can also study Unruh, you can also study Hartle-Hawking.
Yeah, Unruh and Hartle-Hawking are generally kind of similar.
Yeah.
But Boulevard is really where you are putting in the prejudice that something is happening at the horizon.
Yeah, exactly. But even, for example, for Hartle-Hawking, you can have a situation where there are some naked singularities. Yeah. Okay, so what happens, what about this aspect A? What happens to the minimal area surface? We knew that for Schwarzschild, for r prime equal to 0, omega was 0. And that you can also study by, imposing this condition. So you want to actually only impose r prime equal to 0, but for the sake of analysis, we had to also impose this condition that the GTT component of the metric is minimum at the horizon. We want to get rid of it, but for that you need to do numerical computations. And then you can plug in, these conditions in the previous equations. You get a bunch of equations from the previous action. You can massage that equation in a particular way. It's useful. For example, when there is only scalar field present, this equation simplifies a bit. I'm not going into the details, but essentially this gamma and lambda dependent on what sort of fields you have. These are dependent on this A, B, and so on. And so if you only consider n0, the scalar fields contribute, then this quantity, for example, drops out. I think maybe even also this. It's easier to massage the equation then, but you can also do it more generally. I have some backup slides on that. And you can check that the fact that this y square is positive can be rewritten in the form of equality on omega in that case. So what happens is that you will find that in this case, omega is less than some. It actually goes e to the minus s. So it looks, as I was saying, non-perturbative effects. So at least in this case, you get a small modification of the classical horizon, where it's like that picture that I showed you before, where there is a small throat opening up. Yeah.
So now which case we are doing not polar vacuum?
No, it's in the same. Yeah.
Found no horizon, right?
Yeah. There is a small. Yeah. So omega at least. So we found first of all that the Schwarzschild is not a solution. And then we are finding that if you impose the condition of minimality, then for the Schwarzschild, whereas we got, so omega, remember, was GTT
So
of this guy.
0 for the
That's like e to the order e to the minus s.
So it becomes very small but not
Non-zero. Yeah. So you can take this as it is, like an extra entry of what happens in the dictionary of what happens. Okay.
Probably the curvature is very high.
Yeah, this capital R actually blows up.
Yeah, probably very high.
Yeah, indeed. Okay, so in 2D, then we have Polyakov action. We'll again have the same strategy in mind. We'll have some anomaly, and we'll study the anomaly induced effective action. But now the effective action can be exactly written down as we knew for a long time now. We'll use this local form of the Polyakov action which we are talking about. We'll only consider scalar fields in this case. Okay. And then we'll have many choices of states that you have been talking about: Hartle, Hawking, Boulevard, Unruh, and so on. And we'll also consider this dilaton gravity with RST terms, which essentially helps you preserve some symmetries of the problem. And then the calculation, in fact, just becomes quite simple. So we'll start with the classical CGHS model. We have the dilaton field phi and some incoming shell of matter field F. It's known that this e to the minus phi, this plays the role of the radius of the transverse sphere. In fact, that also helps us define an apparent horizon. So this del plus minus phi greater than 0, this gives the trapped points, and apparent horizon then is given by del plus minus phi equals to 0. It's the boundary of the trapped points. In the static situations, you can also convert this relation for the trapped points to a relation on grad of phi whole square. And when the grad of phi of whole square is greater than 0, it's outside horizon. When less than 0, it's inside horizon, and equal to 0, it's the horizon, apparent horizon. And you have a definition of wormhole in this case when grad phi whole square becomes 0 at certain part of space, but it does not change sign when it goes from one side to another. Okay. And the classical solution that yields a static solution, we also know this, which describes a 2D black hole with Hawking temperature lambda by 2 pi. Lambda is some parameter, the cosmological constant, with this mass and entropy. And in light front coordinates, the general solution, static solution, looks like this. So I'll just flash you the space-time solution, some of the space-time solutions that you find. So now if you add Polyakov and RST term, the RST term looks like this, some local term. Then the equation for psi, which came in the Polyakov action, this one, the equation of psi becomes box psi equals to r, and when you solve it, there is this integration constant w which satisfies some equation, and the various choices of w gives rise to various states. For static case, for example, w becomes c over some function of x, and depending on this constant you can have various states. So how the states are computed, so the information of this constant that enters in the stress tensor, if you take the RST and the Polyakov term, calculate the combined energy density, then the generic T0012, meaning T00 for this term 1 and T plus T00 for this from here, that takes this form, and at asymptotic infinity it has this simple form, c plus 2 lambda whole square. Of course it's not there if kappa goes to 0, if there are no fields. So Hartle-Hawking state is usually defined by c equal to 0, but what we found out that there is also another value of c minus 4 lambda for which the asymptotic energy density matches the thermal Hawking radiation, which is how you can pick out the Hartle-Hawking state.
So, okay, what was lambda?
Oh, lambda was this parameter, you know, even in the CGHS. Yeah. Yeah.
So, just repeat what you said last point that you had.
So the last point here, you mean?
After this, so.
Yeah, so I was saying that, you know, how the stress tensor behaves at various locations will help us choose the state. So generically it behaves like this, and it depends on this constant.
And then the next slide, maybe at infinity, if you wanted Hawking, wanted to come out, then
of this energy density, then it chooses these two values of c.
and what are the two choices physically? Both are the Hartle-Hawking state.
Yeah, this is.
Different ways, perhaps, or what?
Yeah, looks like there is some sort of a connection between the two.
The psi field, because it's a sort of auxiliary device in a sense. I mean,
But they do give two different solutions of psi field.
they give two different.
Yeah.
But, you know, in other words, suppose I was just doing the following physical problem. I have one massless field coupled to RST gravity, and the massless field is in the Hartle-Hawking state. Then there's a unique answer to everything, right? But you integrate out the massless field, you get R box inverse R, and you invent the auxiliary psi field, right? Maybe in the auxiliary description you have to
Exactly.
two descriptions, but it's really one physical.
Yeah, I also think that, yeah. For the Boole-Barré state, you choose the situation where the stress tensor is divergent at the horizon and 0 at spatial infinity. And that corresponds to this choice of C. In fact, this is also why Boole states are considered when studying black hole evaporations and these setups, because as soon as you will have thermal Hawking radiation in the boundary, which you do have in Hartle-Hawking for sure, but also in Unruh, at least in Scri+, then they will back react and the asymptotic flatness condition will be lost. So it's only in Boole actually that you have a setup where you have asymptotically flat space-time in the boundary. So I believe that is the reason why people write down in 2D this picture I'll show in a moment, but for Boole state.
It's in Minkowski, asymptotic Minkowski, right? So the asymptotic structure is not ruined by Hawking evaporation, right?
So I'm saying that you can then consider the back reaction of this thermal radiation, and it actually changes from flat. Yeah.
Because I mean, you have a lot of space, right? If the dilaton is encoding the S2 radius or anything, don't you have a lot of effective space? So that,
So this will be clear from some of the equation. I don't know though if I have put that equation in there, but yeah. And then you can also consider, general C states. It's just some definition of states that you can choose that we have worked out for generic values of C. You can also consider what happens to the geometry if you study these states. And of course there is also Unruh state. They are not obtained by choosing such a specific value of C, but you have to impose a condition separately that there is no incoming radiation, but there is an outgoing radiation which is in the Hartle-Hawking state. Actually the analysis becomes very simple when you go to this conformal gauge Sandeep was mentioning. There you take your answers of the metric like this, and after some calculations you can show that the space-time, or in particular this conformal factor phi, satisfies this equation. Okay. Where the factor P is related to the factor C that I showed you before. These x plus x minuses are not, they are related but in a slightly complicated way to these x's, which you had here for example. Okay, so these x's and these x plus x minuses are not like directly related like x plus t, x minus t. So it's P and C relation is simple, but yeah. So P equal to 0 for example will be parameterizing Hartle-Hawking state, P equals to -1/4 in this convention Boole state. For Unruh you will see that this term, although it's there, it's not log of minus lambda square x plus x minus, but only log of minus lambda square x plus. Okay. So frankly speaking, when I was studying these 2D black hole evaporation things, I also thought it was Unruh, but it was this solution, so it was not Unruh. Okay, so well-known solution, Hartle-Hawking P equals to 0. For the static case it looks like for the classical CGHS, but if you have a shock going in, so if F is non-zero, then this singularity is slightly displaced, so the derivative is discontinuous. Still an eternal black hole in equilibrium with its radiation. Asymptotics are non-Minkowski. Sorry, I haven't written down the metric, but it's calculable due to this radiation present. For Boole, this is the typical picture. There you go, your name. No, this reference.
And evaporating black holes. I'm sorry. The whole, anyway, I would say, the whole point was to actually study with entanglement and
absolutely.
How things change when the black hole Hawking evaporates.
Sorry, I put your reference here because I will not be having time to go to entanglement.
But don't quote us as studying the Boole vacuum. That's not correct. Sorry.
But actually I want to talk to you about this also. Yeah.
And also, just I want to say that that paper is with Preskill, so it's Fiola Preskill instrument.
Oh, sorry, I must have missed it. Yeah. Okay. So this is a typical picture for Boole where you have. So if you have some particles in the Boole state and there is no shock going in, then actually the geometry is completely singularity free, and there is a wormhole. That the way, the wormhole I was mentioning, it was grad phi square equals to 0, but the sign of the grad phi square was not changing across the horizon. So that you actually have for Boole if it is the static case. The picture I have not drawn, but it is essentially a diamond. However, if you have some shock present, then it develops some singularities, and it also develops an apparent horizon, and this is the shock, and at some point this apparent horizon hits the singularity, which you can think of as the end point of evaporation, okay, after which the classical description is invalid. It has some outgoing radiation which looks like this. So yeah, as I said, the singularity and the horizon collide at a finite point EP, which can be interpreted as evaporation point. And in the context of entanglement entropy, it was used. We took results from these papers and we studied, but I'll not be going too much into detail in this talk, a similar solution using the technicalities from these papers. And as I said, the static case has a null, there is a null singularity here with a wormhole. Yeah. Null singularity along x plus and x minus. However, if you want to study ghosts in your theory, then it's best to consider them in the Boole state, because it will not be, at least in static case, the way Boole state is defined is that the asymptotic observers do not see the effects of these ghosts. Yeah, I'll be done before this. So you can also study situations where kappa is negative. So for physical particles, kappa is positive. For example, if you have in our setup of RST plus Polyakov, we had something like 24 times kappa amount of scalar fields. But for ghosts, this kappa is negative. And then what you have for the Boole state is that you will have a non-singular and geodesically complete space-time for the static case. But if you have a shock, then it develops an apparent horizon which asymptotes to xh minus, and then there is a radiation out at infinity. And actually, in some recent works, people have shown that you have a similar space-time for dimensionally reduced Einstein-Hilbert gravity, okay, with some matter with negative kappa. So it seems a bit generic, but okay. So what you can also do, you can study both physical and ghost particles together, construct some sort of hybrid state. You can think that you take some kappa 1 numbers of fields in either Hartle-Hawking, Boole or Unruh state, and kappa 2 numbers of ghosts, let's say in the Boole state. And then you can study like what happens if this kappa total becomes positive, negative or 0, and you get some interesting solutions. The dynamics is governed by this equation now, and it is because kappa 2 numbers of fields were in the Boole state. Let's say I have some ghosts in the Boole state, they appear here, and then this equation looks strikingly similar to what we had before. M is the mass of the matter field that was falling in. In this case, if you take some static situation with Hartle-Hawking state for physical particles and Boulware state for ghosts, then you will again find out some non-singular geometry, but with a horizon replaced by a wormhole throat, which is very much like this example that I gave in the very beginning, where the metric component, the GTT component of the metric is minimum. However, it's not the point where grad of phi square goes to 0. So there is this distinction between two types of quote-unquote wormholes, which one calls usually type 1 and type 2 wormholes. So it is of this type that the GTT components is minimum. And then there is some radiation out to infinity because there are some particles in the Hartle-Hawking state. So this radiation depends on kappa 1. If you have a perturbation, then it develops once again a horizon-like structure. It is completely singularity free, and then there are some radiations coming in depending on kappa 1 and radiation going out depending on both kappa 1 and kappa 2. In fact, the fact that there is this kappa 2 numbers of particles in the outgoing radiation, if you calculate how the outgoing radiation entropy behaves with time x minus, then you will see that it has a page curve like behavior. It grows initially and then it falls down. So it's kind of a toy model for as if there is a entropy growth and decrease, although there is no evaporation here because the horizon is eternal. You can get rid of this incoming radiation by going to a perturbed Unruh-Boulware state, in which case you will have the similar structure for similar expression for the outgoing Hawking radiation, but there is no ingoing thermal flux. Okay. So as a conclusion, this is just a table for your visual pleasure for the static cases. We try to enumerate the cases where you have some particles, some ghosts in various states, maybe even in the combinations of some physical particles, non-physical particles, they being in different states, and found how the geometry behaves in each of these cases, whether they have a wormhole or not, whether the geodesics are complete or not, whether the singularity exists or not. And okay, in 2D the results can be found out really rigorously, but in 4 dimensions we could only do a near horizon analysis. Actually, in 4 dimension, the fact that this omega is bounded by omega 0, which was like e to the minus s, you can also think of it as a bound on what was the temperature of a Schwarzschild geometry, and one can show that the temperature is very low. And so there were some papers after our paper came out which talked about some experimental signature of such situations. And of course everything boils down to the known black hole case in the classical limit. Okay. So with that I think I'm done. Thanks.
So K1 and K2?
Yeah. So so the kappa appears here also in Polyakov, and for in general this kappa is n over 24 for a multiplet of n scalars, but if you have some ghosts they come with negative values of kappa. So I think for in the
It's like the central chart.
Yeah, it's like the central chart. So you can have like I think minus 26 for ghosts in string theory, Liouville string theory, Yeah, so anyway, so if you have two types of fields, you can write down, superpositions of actions for both fields, one with kappa 1, which is positive, and another with kappa equal to kappa 2, which is negative, and study the entire action and its corresponding solutions. Yeah.
In 1+1 dimensions, if you have a static geometry and if you have boundary conditions for the stress tensor, just boundary conditions with no flux or something, then if you have no flux in DRT, that will already rule out under if you just demand that. And then if you have the trace anomaly condition and conservation of stress tensor, you have a couple of choices coming from integration constants that either give you Boole or, so depending on, this is an argument due to Israel and Debajyoti. So I think that, so this choice is somehow ultimately a choice. I think. It's like you can't really.
So are you saying that, for example, the way I chose the states is not the unique choice?
I'm saying that
in literature other choices exist.
There are some choices being made, like choices about the incoming fluxes and
Yeah. So there could be. I haven't studied that particular paper, but my choices was that. Yeah.
I agree. But the underlying message seems to be that there is, like one has to. Yeah, okay. You can just sacrifice the principle of equivalence as you choose. That's, of course, but I'm just saying that if you want to bring it back and connect with classical general relativity in some way, then we also have to have a.
But I'm it's true. I agree. I'm just saying that these things are. People do study them. For example, this paper by Hartmann and Strominger, they were actually studying. In the RST model, if somebody asks you how to, form a setup which has a black hole evaporation process, ask questions whether page curve is there or whether islands needs to be there, then you actually need.
The moment you put in a firewall, you get a picture. So the question
is, that's true, indeed.
What you have, if you put something at the horizon, you'll immediately get a picture.
Absolutely.
But the question is, how do you get the principle of equivalence also, at least in some limit?
I agree, and that's what you also worked on, yes.
Yeah, so that I think is,
Since you're about this, let me just make one comment. Sorry, because I have to set history right. In the paper of Fiola, Preskill,
you were not,
with me here. I haven't read the Andy paper after that, but in that Fiola, Preskill, Strominger 3 paper, here's what we showed. Okay, with all the I's dotted. Before Cardy developed his so-called formula, called now attributed to him, about how to compute the entanglement entropy for some region in the presence of conformal matter, we derived that formula in 1994. Okay, along with the student of Halsey. Anyway, so we had that formula. We then took, the Unruh vacuum, which was produced by throwing in something which forms a black hole. We watched the black hole evaporate. The horizon receded like it should, and we computed the change in entanglement entropy, first principles, and we showed that there was nothing like the page curve, it went up and up. In other words, we were just seeing what Hawking told us,
Yes.
That's the content of that paper, but it doesn't ab initio first principles from entanglement. There's no Buhler stuff, it's a physics. Okay, sorry, I just had to say that.
No, thank you. I must have given a wrong message actually.
What Hartmann, Shaguli,
so they actually, they studied this this equation, which you get for P with P equals to -1/4. So that you only get for Boole.
Okay, so they might have studied that case.
And they did indeed took some equations from your paper. I guess that's why I cited
the same
it.
System. I don't know why they studied Boole, but okay, they studied Boole. But you don't have to do that, and then you don't get anything like a firewall. If you take the Hawking vacuum or Unruh, you get a nice horizon.
Yes.
And you get Hawking evaporation and so on, and the build-up of entanglement.
Yes. So for example, in this Boole array picture, you do get a singularity, a nice horizon, and you can study Hawking radiation here also. You don't have a firewall.
In the Boole array.
When you calculate the back reaction. So initially, the way you set up the problem you have a firewall, a bad thing happening at the horizon. But when you study its back reaction effects, it can give rise to a physically reasonable setup. That's all I am saying. Yeah. In fact, sometimes it changes the geometry so much so that you don't even have a horizon or singularity, or sometimes you do have a singularity, sometimes you don't have a singularity. Sometimes you have a horizon, sometimes you don't have a horizon. So that's all I wanted to enumerate or list out. Yeah. In that, yeah, so you can choose just one set of fields, or you can set two sets of fields, and then things are more intricate. And then, for example, one good thing that we found out was that, as I said, that in one setup we had this page curve like setup, where you could have some growing entropy in the beginning and then decreasing entropy of radiation. For example, this paper, as I said, Hartmann's paper, they studied the Boulware setup. They took some equations for entanglement from Sandeep's paper, because as he said, it's essentially the same system. And then they could show that if you don't consider islands, the entropy will grow and you will not get page curve. And they calculated that, yeah, with islands you do get a page curve. So it has these utilities. So yeah, and I think that the reason they choose Boulware is because then in the horizon, in the boundary, it's asymptotically flat. Yeah. But I haven't talked to them, so I don't know exactly.
Maybe we can have a discussion sometime.
Yeah, okay, all right, thanks.